Welcome to the Develop Yourself podcast, where we teach you everything you need to land your first job as a software developer by learning to develop yourself, your skills, your network, and more. I'm Brian, your host. I'm recording this episode the day after the U.S. presidential election, and there's a 50-50 chance that you woke up really happy or you woke up really, really upset about the election. I'm going to tell you a little anecdote before we get into the real meat of this episode, which is about data structures and algorithms in real life, which will hopefully take your mind off of whatever you're thinking about, or at least illuminate some things about data structures and algorithms and show you some real-world practical examples of them that I think are pretty interesting. But before we get to that, I know there's probably a lot of emotion around the election and things that happened, and I'll say this. When I moved from Oakland, California, about 10 years ago, where I lived my whole life, I went to a very liberal arts school in Los Angeles. Basically never really ran into conservatives at all throughout my whole life. When I moved to the suburbs about 10 years ago, I moved to a very conservative area. My neighbors are Trump supporters. Some neighbors are Biden or Harris supporters. It's a diversity of political opinions out here, much more so than living in Oakland, California, which is about as liberal as you could imagine. One thing I learned from living around people with differing views is that ultimately, it sounds corny, but we're just people. Whether you believe in certain political ideology versus the other, I've had nothing but great interactions with all my neighbors out here. I'm one of the only people that looks like me in this community, and I've had nothing but respect and made friendships with people that I honestly never thought I would have. So I know that the media and news can get us into this feeling of like us versus them, or these people hate us, and people are just ultimately people. I really have a hard time I don't believe that people that vote a certain way hate other people. I just don't. I know that some may, but I know the majority don't. It's why we as a nation get along with each other. It's why I believe that you can change your life. You can learn something, whether it's coding or some other high-paying skill, and completely transform you and your family's life in this country. It's an amazing thing about America, and I know it won't be lost. And I hope that no matter what's going on in the larger national stage, that you continue to focus on yourself, your community, your family, and what you can do to better your own life. Anyway, enough with that rant. Let's get down to what I'm actually here to talk about: data structures and algorithms. Good segue, huh? You like that? You like how I just pivoted directly into that? Smooth as butter. Anyway, I'm a self-taught developer. I also went to a coding boot camp, right? Data structures and algorithms are things that I wanted to avoid. And I've heard a lot of developers online say this. They just don't want to learn this stuff. Even worse, you go to comments online and they say things like, I'm never going to use this stuff in real life. No one needs to know algorithms and data structures in order to be a successful software engineer. And here's the thing. They're not wrong, honestly. You can be a software engineer, have a pretty good career, and you'll never really need to come up against data structures and algorithms explicitly, but you will use them all the time, if that makes sense. You're using them and leveraging them, whether you know it or not. The libraries you use, the databases you use, the patterns that the senior software engineers use, they're often going to leverage these things, and you're using them, just not with your own knowledge. So if you want to deepen your understanding and become a better software engineer, I 100% think you should know some data structures and algorithms. I kind of resent it just a little bit when I go online and I hear people saying these things like, you don't need to know anything at all. All you need to know how to do is write some React and JavaScript, and then you'll get $100,000 a year job or $200,000 a year job. And to be honest, I've met people that do that. It's not generally the case. And knowing these things not only gives you a deeper understanding, it helps you avoid reinventing the wheel by understanding patterns. When you have patterns to do things, now you can deploy them and employ them when you see similar problems. That way you're not just reinventing the wheel all the time. So why do people not want to learn this stuff if it makes their life better and helps them write better code? Well, I was one of those people. I didn't want to learn it because it was just intimidating, to be completely honest. I was like, well, I kind of get JavaScript. I can compose some code to work to get to the desired functionality I need to get it to, right? So you want a button that I click and it does this. Cool, I can do that, right? That's my job. Why do I need to know this other stuff? It seems like it's mathematics heavy. I'm really nervous about that. Maybe it's just not for me. It was also just really conceptual. I'm like, well, what do you do with these algorithms? Are these just for passing interviews or something like that? In that case, maybe I don't need to learn them at all. I'll just go to companies that don't ask those kinds of questions in the first place. Also, when I started learning to code, there was no industry that was built around just learning data structures and algorithms. Nowadays, you have all sorts of options, which is even more interesting to me that people still don't want to learn this stuff despite having so many options out there. And whether you want to go to Google or you just want to open up and expand your horizons and ability to interview other places, that alone is a good reason to learn data structures and algorithms. And that's actually why I started learning them, because I got an offer to interview at Google. And I thought, well, damn, I better know this stuff. I went in, completely failed, and then I doubled down on learning data structures and algorithms. I got pretty good. I ended up getting back to Google, getting to the final rounds, getting to Facebook final rounds. Didn't nail any of them, but I didn't fail them. I didn't bomb them at all. I actually did pretty well. I was shocked how well I did. And this is coming from a person that was like, I'll never need to know this stuff. I don't want to know this stuff. I'm scared. I'm not good at math, and I don't think I can do it. Now, what are data structures and algorithms exactly? Think about this. If you want to bake a cake, what would you do? Would you go into the kitchen and just start putting together flour, water, random stuff in a bowl, and then you just kind of hope for the best? You could, and maybe you'd even make something that resembles a cake. But there are algorithms out there, and they're like recipes. And these recipes have been perfected and crafted over hundreds of years, right? Or maybe dozens of years or decades or whatever. And you can use that to make a cake, right? There's a recipe for that cake. You can pick a recipe off the shelf and they'll follow a similar pattern. You can make many types of cakes, right? But they all follow a similar pattern. They're probably going to use flour, probably going to use water. Maybe you're going to use some chocolate because it's a chocolate cake. And you're going to take this recipe or this algorithm and you're going to bake the cake according to this set of instructions. It makes your life easier. It reduces the cognitive overload that you have because you're not starting from scratch. The same thing can be applied to software. And you hear about algorithms all the time. My video tanked on YouTube. It was the algorithm. Oh, the reason I saw that is because of the algorithm. The podcast, terrible because of some algorithm, some recipe, some pattern, some way to determine what you might like and present it and feed you with that information. These algorithms are just step-by-step instructions that can be really complicated or be not so complicated that help us achieve a goal, just like a recipe. And you can use algorithms for things as small as sorting an array of data or as large as finding your path from point A to point B. Think about Google Maps. So what I want to do in this episode is break down algorithms and data structures that make up our world, the ones that you come up against all the time without really knowing it, and the data structures and algorithms behind those things so you can hopefully look them up on your own, figure out how they work, and stop being so freaking nervous about data structures and algorithms. So we went over algorithms a little bit. Really simply, a recipe, a repeatable way to achieve a certain thing. So whether you're trying to find a path or bake a cake, add some numbers, there are ways to do these things. There are algorithms to do them. Data structures are a little bit different, and they are what they sound like. They are ways to literally structure data. Why do you want to structure data? Let's take an example of something that I'm almost certain you've used, Excel. Everybody's favorite or least favorite tool, right? You have an Excel spreadsheet. You have rows and you have columns, and that data is organized in a tabular way. It makes it easy to look at. How else could you organize it? I mean, it seems intuitive. We look at that and say, well, yeah, well, how else could you possibly put that together? Well, you could put it together in a big list, right? An unorganized list. You could have the rows and columns in like one line, and you could have all the other data in another. And then you could figure out how they're related somehow. That would be a really stupid way to do it, right? It'd be terrible. Like, why would anybody do that? Or you could just put it on a piece of paper and write it out all by hand. These are types of ways you could organize the data. The really efficient way to organize it is how it is in the Excel spreadsheet. It makes it really easy to find a row, a column, look at E4, and you see exactly what's there. So data structures are ways that we can organize data that makes it easier for us to retrieve, look, and search for data. And in computer science, there are a few really, really common data structures: trees, stacks, queues, and linked lists and graphs. Hey, I hope you're enjoying this episode, and if you're interested in becoming a software developer, learning how to build complex software, and actually get hired, join me at Parsity.io. If you're serious about joining, just schedule a call with me by clicking the link in the show notes below. Hey, I hope you're enjoying this episode, and if you're interested in becoming a software developer, learning how to build complex software, and actually get hired, join me at Parsity.io. If you're serious about joining, just schedule a call with me by clicking the link in the show notes below. We're going to go over most of these data structures with some real-world examples, not high-level conceptual stuff. That's for interviews only. We're going to look at how do people actually use these things in real life so you can see that they do have some practical utility. Let's start off with one that's really interesting that I'm sure you haven't heard of, but you've almost certainly used, and you probably used it today. It's called a trie. You can also call this a prefix tree. So how is this thing used? Auto-suggest. Next time you go to Google or you're typing in something in your browser and you type in C and then A, and then it tells you, hey, are you typing in cat or catalog or category? It'll tell you the next series of letters based on the previous series of letters that you typed, even if you don't type it correctly necessarily. You don't have to spell the word right for it to give you these suggestions. So how is it doing that? How does it know that after you type in C and A, you might want to type T or TE? If you type in CAT, it might give you catalog or category. And this is almost certainly using a prefix tree or a trie under the hood. What a prefix tree is, it will store a set of strings, a set of letters, characters. Each node in this tree represents a character. So you might have A as the first node, right? And then what comes after A? What is likely to come after A? Maybe T, maybe L. It'll look at the common letters that typically come after a certain character. So if you look at C, for example, it says what typically comes after C, and we'll have all those possibilities connected to C. So you type in C, and it will begin offering you like, well, here's typically what comes after C. Oh, what typically comes after O? Maybe another O for cook or something like that. This is a tree-like structure, meaning that each node, the letter, will have other children, and these children will also be nodes, and they will have other letters connected to them. So you have this tree full of letters that basically helps you suggest things based on your specific history and also the history of billions of other searches. So they can compose all the different combinations that they see are really, really common, even misspellings. They'll say, okay, what usually comes after C? Well, sometimes somebody might fat finger the keyboard or something like that. Instead of typing O, they'll type K or L or P or I or whatever, something that's near the letter O. So they may have misspellings as well that are in this prefix tree, which will still get you to the correct word that you're trying to get to because they have billions of searches, maybe even trillions of searches at this point in their Google search history. By the way, this stuff is not like secret proprietary information for the most part. Most big tech companies will write papers, documents, articles that will explain how they do these things at a pretty high level. In fact, if you want to read about system design and kind of how these major tech companies do things like news feeds or auto suggests or large searches, you can read a book like System Design by Alex XU, and that'll teach you a whole lot about what's really going on under the hood at a high level. It's language agnostic, meaning you don't need to understand JavaScript or Java or C# to learn it. It just tells you at a high level, like here's kind of how they build out these things. Here are some of the structures they use under the hood. And here's the general flow of how this works. It's really cool. And it's a pretty short read. I really like that book. And he has a site, Byte Go, as well. You might want to check out. Not sponsored at all. I don't think Alex Zu knows I exist, but I think he has some really good material out there if you want to go further. The next data structure is a stack. And when you think of a stack, think of a stack of plates, right? You have a stack of plates. You're organizing the plates in the only way you can really organize plates, right? You can't just put them side by side by side. That would be weird, right? You could do that, but it would just take up a lot of space. So you stack up the plates. How do you get a plate off the stack? What are you going to do? Where are you going to grab it from? The very bottom? That'd be terrible. You'd ruin your stack of plates. You might knock the whole thing over. So you're always going to grab that top plate, right? That makes the most sense. You're going to grab the plate from the top. That is a data structure. That is the stack data structure. The first thing in is the last thing out. The last thing in, that last plate that you put on top, is the first one you're going to grab. It's basically the opposite of how a line works. If you're in a line of humans, which we'll get to in a minute, which is actually represents another data structure, the first person in the line is the first person out of the line. If the people are normal people and they're not terrible people, right? Now, a stack is the last thing that's in that stack is the first thing that's going to come out of the stack. Now, why do you care? You've probably used a stack if you've used something like Google Docs, right? Or Microsoft Word or whatever. When you're writing a document and you want to undo some recent thing you did, like you press Command Z or Control Z to undo something, that action is likely being stored in a stack under the hood. So when you want to undo the last action, it means the last thing you did will be the first thing that comes out. So a stack will usually be used to store all your different actions, and you'll pop something off of that stack and say, oh, let's undo that action. And if you want to redo it, it'll add it back on. It'll be the first thing on top of the stack. So if you undo and redo, you are undoing and redoing the top of the stack. If this was using a queue data structure, which is like a line, so you think of a line, a queue. If you're not from the US, you probably use the word queue when you're talking about lining up. I'm a true American citizen, and I'll never use the word queue when I'm talking about lining up. But a queue would be first in, first out. That wouldn't really work so well in a document, right? If you're undoing the very first thing you did, it would be super confusing. That would not work at all. So a stacked data structure makes the most sense in this case because it perfectly achieves what we want to do when we erase something or we want to undo an action. And by the way, these data structures are language agnostic. So whether you use JavaScript or C#, Java, Ruby, whatever, Fortran, COBOL, it doesn't matter. The concepts are going to be the same. The implementation may change. For example, if you're using JavaScript, a stack you would use an array because we don't have a stack data structure that's just native or out of the box with JavaScript. It's not some hidden data structure that you can use. So what you'll have to do is use what you already have. So a stack or a queue, you could use an array. And all you need to do is change how you interact with that array. So if it was a stack, you'd be looking at the last thing whenever you want to pop something off of it. If it was a queue, you'd be looking at the very first thing and popping things off of it. This is often what you do in an interview when they say, okay, let's create some sort of stack data structure. And all you'll do is basically wrap around the functionality that an array already has and create methods that only look at the beginning or the end of the array, depending on what kind of data structure you're trying to use. For a tree, you may think, well, how do I achieve something like a tree? Well, think about a data structure in JavaScript that can have one node or one item that can have multiple items connected to that one item. I think of an object. And that's a really good way to represent a tree. So you can represent these data structures with the things you already have. You can build them. Now, in some other languages, you have these out of the box. In JavaScript, you do not. Speaking of trees, as a JavaScript developer or a person that works on the web, trees are everywhere. They have a hierarchical data structure. So they have these nodes that we've talked about that are connected to other nodes. And they have this parent-child relationship. So think about this. I'm a parent. I have multiple children. My children could also have multiple children connected to them, and their children could have multiple children connected to them. We see this all the time. If you go to like a house or an old school picture, you have an old school family tree, the family tree structure. That tree structure is also super common throughout the web and software in general. In fact, the tree structure really is just common throughout human society. I mean, again, back to the idea of the family tree. This is a data structure that represents a lot of what we see in real life, which is common with all the data structures. They often mirror something, some phenomenon that we see in the actual real world. And when you think about a web page, for example, a web page is basically a tree. You could have a HTML element, and under that HTML element, you'll have many children. You'll have divs, and that div could be a parent element. And what's under that div? More children. The div could have tags, p tags, and those can have children under them. They can have text or further p tags or further div tags or things like that. It creates this big tree. And so when you're doing something like scraping data on the web, you're often following tree-like structures and figuring out where is information located. And if you zoom out a little bit, a whole website could be considered almost like a tree. You have a home page, which could be the root of the tree. Then you have various pages and subpages as children. And the way you navigate it is by going through and looking at the root and then diving into the children and looking further into their children so you can go really deep down one path in the tree. Now, there are different types of trees. We talked about a prefix tree. Here's one of the most common trees that you'll be exposed to. Binary search trees. This is taking the idea of a tree a little bit further to help organize the data. Binary search trees help you cut in half the amount of time it takes to look for certain data. So binary search trees are organized in a certain way. They're just trees where you have a parent and then you have a node, but there's a certain rule. One parent can only have 2 children, right? They are limited to 2 children. You can't have more. Binary. Think about bicycle, 2. So you have 2 nodes to each parent. And on the left side, the left child will always be less than the value of the parent. And the right side will also be more than the value of the parent. So if you have numbers, 1, 2, and 3, and you're representing them in a binary tree, you may have the root node be 2. And what's going to be on the right? What has to be on the right? Well, if the right side is always more, then 3 has to be on the right side of 2. And that means 1 has to be on the left side of 2 because the parent has to be greater than the left side and has to be smaller than the right side. Now, imagine if you're looking for data in a massive tree. Let's say it has 10 layers and, thousands of different nodes in there. What you could do to search for a certain value is you could look at every single node. Or because it's a binary search tree, you can look at every single node and decide right on the spot whether you need to go left or right because you already know. Well, if it's larger than what I'm looking at, I need to go to the right. If it's less than what I'm looking at, I need to go to the left. Very simple, right? So databases will often use this tree structure under the hood to have super fast lookup time. So if you need to look up a value, storing it in a binary search tree, if you need super fast lookup times, could be really important. Now, it's true that it's very rare as a developer that you just be implementing a tree or a binary search tree from scratch. And I actually had to do something kind of like that at a previous company where I was working. We were creating this proprietary language. It was a really cool project. I didn't really understand a lot of it. It was way outside my depth. It was beyond my depth at the time as a developer. And we had to create this tree-like structure that would make searching really, really fast. It kind of resembled a binary search tree. And I was really glad at the time that I knew a little bit about trees and the benefit of using them for fast lookup and searches and things like that, because it made more sense to me why we were doing it this way, why the developer had decided to go with this type of structure to represent this query language that we were building at the time. So when people say, oh, you'll never use this stuff in real life and only in interviews, that's not quite true. I mean, that's one time, honestly, in my career that I had to explicitly use that type of structure. But I mean, I had to do it. And thank God I actually knew what I was doing. I could have learned it on the spot for sure. It wouldn't have been like I was screwed, but it came up. Now let's end at one of the most common data structures you're ever going to see and the one that really makes up a lot of our world, graphs. Graphs are kind of like trees where you have a node, but then you have vertices and they're connected by edges. And these edges will represent relationships or connections to these other nodes within the graph. And you'll probably already think, okay, this sounds kind of familiar. Relationships, graphs, social networks, right? You have nodes, which may be you or another human. You have friendships, which are your connections. These are the edges. And then we have people at the edges of these graphs. They spiral out where your connection may have edges to other people, like their family, their mom, their dad, their friend, their buddy from high school. They have first party connections. And then beyond that, so you're connected first to the people in your circle. You're connected to your mother, your father, the person down the street, the guy that you buy milk from. Who are they connected to? When you look at their vertices, you look at those edges that spread out to the next layer, who are they connected to? And who are they connected to? And then you keep spreading out. And this is how social networks and graphs and human relationships and even maps kind of work at a high level. And we use this type of data structure in all sorts of different apps, Twitter, Instagram, LinkedIn. You're connected to a lot of people, and you may be connected to people in the first layer that you know. These are your first party connections. And then you have people in these second layers. So this is really fundamental in modeling a social network. And then you have specific algorithms that are used to search these graphs, which is important because how do you know who's your first party, your second party, your third party? On LinkedIn, when it tells you this is a second party connection, or oh, this is a third party connection, there's some sort of algorithm that they used to understand how you're connected to other people. And when Facebook or Instagram recommends like, hey, I think you might know this person. We see that you're connected to somebody that has them as a first party connection. The chances are you probably know them as well. Maybe you have 2 or 3 people that are connected to this person as well. So we see that you're connected to 3 people who are also all connected to this one person. We're going to make the assumption that you may know them as well and then recommend them to you. That could be an algorithm. It could even do something as simple as saying, if you have this many connections, like if you have 4 first-party connections that are connected to a second-party connection, we're going to recommend them. Or it could even take it down and say, you know what, that was too strict. Let's take it down to 2. Let's take it up to 5. And we can see and refine our algorithm based on how our users respond. And if they say, oh yeah, I don't want to know that person, or oh, I don't know that person at all. Who the hell are they? Or if people start liking them and saying, oh yeah, I know that person for sure, then the algorithm becomes more efficient and they can refine it over time. Now, if you took Lyft or Uber or some car share service recently, they almost certainly were using a graph, right? Because city streets are represented as graphs. You have ways to get from point A to point B. And the way they can figure out what is the most efficient way to get you from point A to point B are using some famous algorithms out there. There's a few that you might have heard of or that you should be familiar with at least. Dijkstra and the Traveling Salesman. Dijkstra, D-J-I-K-S-T-R-A. Tough name to pronounce, but Dijkstra is the name of the algorithm. It's a graph algorithm that finds the shortest path from a source to an output to all other nodes in a weighted graph. Very complicated way of saying it looks at a graph and it has weights. The weights could be, how long it will take to get from point A to point B, or the distance from point A to point B or something like that. So it probably will have things like distances that represent here from point A to point B is 2, right? From point B to point C is 3. But from point A to point X to point Z is, 10. And it will look at all these different possibilities and tell you, well, the shortest distance to get you from this node to this other node based on all these weights and all these possibilities is taking this specific route. Now, that is a really cool algorithm because it can be used to really shorten the time it takes you to get to a certain point. So if you're using a GPS system, it understands what's the shortest path between these locations. The traveling salesman problem is a classic optimization problem where you're looking for the shortest route to visit a set of cities and then return to the origin city. This is a problem modeled after a typical real life problem. Let's say you're a salesman and you're selling vacuums in the Midwest or something like that. You start at your house in Ohio that morning, and then you go hit up 4 or 5 states in different cities around those places. You say, what's the best path I can take to hit these 10 cities and get home so I can finally be home and eat my pot pie or whatever it is this dude's eating at the end of his salesman day? Classic problem. We're using logistics and we're trying to think, I need to get the shortest route to visit all these cities and then return to my origin city. This is actually still used in logistics, manufacturing, circuit design, airplane, planning routes for flights where they visit multiple airports and they want to minimize their fuel costs. So these aren't just really obscure things you need to know for only going into interviews. These can actually be really helpful when you want to model real life scenarios and figure out how to best optimize for them. So how do you learn this stuff? I have an episode going over that, like how do you actually learn data structures and algorithms. And I think the best way, honestly, is to pick a few of the really big ones that I've just kind of gone over here, like trees, linked lists, queues, stacks, and learn how to write them in the language that you feel comfortable with, and then look at how to use them in a practical way. So look up examples of how to use them, but very first, just start with actually building them from scratch. Saying, okay, I know some JavaScript. Well, how do I build a stack? Cool. How do I build a queue? Cool. How do I build a tree? Okay. Now that you've built these things, look up how do you search and get data from these particular structures. So once you build a tree, you think, well, how do I search it for the largest value? How do I search it for the smallest value? How do I search it for any value? Now you're going to be prepared for your interviews. You're going to know how to leverage these data structures, and you're going to see them more and more as you encounter them in the quote unquote real world. I think these are fun to learn. I think there's a ton of great resources to do them. And I also don't think you need to overcomplicate it. At the very worst, you'll be prepared for way more interviews, so you won't have to purposely avoid whiteboard interviews. And now you can go into them way more confident. And if nothing else, it's just kind of fun to learn. I always hope that's helpful, and I'll see you next week. That'll do it for today's episode of the Develop Yourself podcast. If you're serious about switching careers and becoming a software developer and building complex software and want to work directly with me and my team, go to Parsity.io. And if you want more information, feel free to schedule a chat by just clicking the link in the show notes.